So this is the notes video for the second part of section 10.3, which is about solving situational or word problems involving exponential decay. This is going to be a lot like what we did yesterday, except that now, since we have decay happening, each problem, the rate is going to be subtracted from 1, since decay means we're decreasing. Just like with exponential growth, that initial amount is going to be represented by a, or the first number in each equation that you write out. If your rate is given as a percent of decay, we need to make sure that we write that percent as a decimal, so move the decimal 2 places to the left. And then the x in the exponent, that's going to be represented by the amount of time or time periods. In addition to the word decay, you might see other words in these problems that represent decay, or that the amount is getting smaller. You might see words like depreciate, decrease, or less. So make sure you look out for those words that indicate you're working with exponential decay. So our first example here is in 2004, the population of Australia was decreasing by 0.8% each year. So first we want to find the growth factor and then answer the question what the projected population would be in the year 2010. So working with this general equation to help us find the growth factor, we know that the starting amount, or A, is going to be given by that first population number from 2004. So that 17,800,000 can replace A in the exponential decay formula. And then our rate is 0.8%. So if we move that decimal 2 places to the left, that would become 0.008. The x, so our exponent, is about how much time has passed. If we go from 2004 to 2010, that's a total of 6 years. Now, the first question asked, what is the growth factor? So the growth factor is the result when we subtract our rate from 1. So 1 minus 0.008 is 0.992. So that identifies the growth factor for us. Then part B asks us what the projected population would be. And for that, we need to just calculate this. So if we raise 0.992 to the 6th power and multiply by 17,800,000, we would end up at 16,962,507. Now, this growth factor makes sense. It's less than 1, which means that as we multiply by a number less than 1, we are going to go down. We should expect that, since this is an exponential decay problem. Also, 0.992 means that we're keeping 99.2% of the population every year. So that's the same thing as decreasing by 0.8% every year. Next example says you bought a car for $28,500 in 2005. What is the value of the car in 2008 if it depreciates at 13% each year? So let's start with the initial amount. So that is that 28,500 number. And then the rate is given as 13%. So if we move that decimal 2 places left, we'd end up at 0.13 for the rate. And we are talking about a time period from 2005 to 2008, and that is 3 years. As we first subtract 1 minus 0.13, that gives us 0.87. Well, if we lose 13% every year, that's the same thing as keeping 87% every year. So that growth factor makes sense. Now, calculating results in a total value of $18,767 after 3 years. So that is percentage decay. There's another type of exponential decay that's really common, and we'll talk a little bit more about this tomorrow. But that is something called half-life. So half-life is something that all substances have. A half-life of a compound or element is a measurement of how long it takes for one half of the compound to break down, which means that after the half-life period, only half of whatever substance you're talking about is left. So that means that we're multiplying by 0.5 or multiplying by half every time period. A is still the initial or starting amount. For a half-life, whenever you see the words half-life, the growth factor is always going to be 0.5. The time is where this gets a little bit tricky. Really, what we're going to be looking for is how many half-life periods have passed. So we want to know how many times did the starting amount get cut in half or multiplied by 0.5. To figure that out, we're going to be not using the half-life itself. We want to know how many times has the half-life happened. So we're going to be dividing the total time by the half-life. So our first half-life example, it says an isotope of cesium-137 has a half-life of 30 years, which means every 30 years, the starting amount gets cut in half. If you start with 20 milligrams of the substance, how many milligrams will be left after 90 years? And how many will be left after 120 years? So thinking about the half-life formula, our rate is always 0.5 with half-life. We started this problem with 20 milligrams, and then we want to figure out how many half-life periods will go into our exponent. So the half-life is 30 years. There is a total of 90 years that has passed. So if you do 90 years divided by 30 years, that gives you 3 half-life periods have passed. So the exponent would be 3. So calculating gives us 2.5 milligrams of that initial 20 that would be left. If I divide 20 in half 3 times, 20 divided by 2 is 10. 10 divided by 2 is 5. And 5 divided by 2 is 2.5. How many would be left after 120 years? The same starting amount and the same growth rate. But 120 years divided by a half-life of 30 years represents 4 half-life periods have passed. So the exponent would be 4. And then calculating gives us a result of 1.25 milligrams, which is, again, one more half-life. So one more time, 2.5 is divided by 2. So that gives us 1.25. Finally, radium-226 has a half-life of 1620 years. Half-life can vary wildly from element to element and substance to substance. So it starts with write an equation for the amount of radium remaining if you start with 4 milligrams and X number of half-lives have passed. So we're starting with 4, and we don't know the number of half-life time periods. So that first equation is just 4 times 0.5 to the x. How many would be left after 4,860 years? Same starting amount. But now, if it's a total of 4,860 years divided by the half-life of 1,620 years, that gives us 3 total half-life periods. So again, I divided the total time by the half-life, and that gave me my exponent. 4 times 0.5 to the third power is 0.5 milligrams. So that is exponential decay. Please give the 10.3b assignment in your homework packet a try, and then we'll deal with any questions questions that you have in class tomorrow. Thank you.